situation. In a calm and stable air mass, without lift, sink, or wind, the paraglider's trajectory will not be disturbed. It'll approximately fly at the speed specified by the manufacturer. The same applies to the sink rate, which also figures in the technical specifications. In this example, the ground speed and the glide ratio are roughly the same as the airspeed and the lift-to-drag ratio. Second example. The paraglider is flying into a 15 km/h headwind. In this case, the horizontal ground speed is reduced. It can be easily calculated by subtracting the wind speed from the paraglider's airspeed, since they are moving in opposite directions. 37 minus 15 equals 22 km/h. Though its ground speed has decreased, the paraglider still falls at the same speed. Thus, for the same altitude, it runs a shorter distance. Its glide ratio has decreased. A new example. The headwind is now 35 km/h, almost the same speed as the paraglider, which, by the way, could end up being rather dangerous and should therefore be avoided. In this case, the ground speed is almost zero. The paraglider continues to descend at the same speed and appears to be falling vertically. Know how to get your bearings and observe these phenomena. Adapt your flight plan accordingly so that you're sure to make it to the landing field. Let's take a look at how flying with a tailwind can affect your trajectory. As you might have guessed, a 15 km/h tailwind will increase the paraglider's ground speed. 37 plus 15 equals 52 km/h. Falling at the same speed as before, yet moving faster, the paraglider in this case will cover much more distance. The glide ratio has increased. Here's another example, this time with a 35 km/h tailwind. The paraglider's speed will be close to, if not more than, 70 km/h. This is why cross-country flying is usually done on days when wind conditions help the pilot reach his destination, and also why pilots always land into the wind. Wind is what causes an air mass to move. Depending on your orientation, these movements can increase or decrease your glide ratio relative to the ground. They also cause drifts that you need to compensate for in order to maintain your heading. Besides the wind, other factors disturb an air mass and cause it to move vertically. Flying through a thermal lift or a downdraft can also influence your trajectory. As a reference, let's start with the trajectory of a paraglider in a stable air mass. In the absence of lift or sink, the sink rate is approximately 1.2 meters per second. In this case, the trajectory corresponds to the canopy's technical specifications, which means that its glide ratio is the same as its lift-to-drag ratio. Here's a new situation. The paraglider comes across a warm pocket of air called a thermal that is rising at 3 meters per second. As he enters into it, he is carried aloft by the rising air. His altitude will increase and he'll be able to use this additional fuel to cover more distance than if he were in a stable air mass. Whilst the glider is in the thermal, it continues to descend at its sink rate of 1.2 meters per second. But, since the air mass it is flying in is rising faster at 3 meters per second, the paraglider will gain altitude in relation to the ground. The climbing speed will be 3 meters per second minus 1.2 meters per second, which equals 1.8 meters per second. You may have already guessed that in the opposite case, when the paraglider comes across a downdraft, his sink rate will increase because he is falling in a mass of descending air. He'll cover less distance than under stable air mass conditions. Here's another example where the wind influences the trajectory. The paraglider is flying in a crosswind. In this first case, the paraglider wants to fly over point A. However, he neglects to take into account the direction of the wind and ends up drifting off course. He'll have to correct his heading. With his new heading towards point A, he is now facing a headwind. As we've seen earlier, this situation drastically reduces his glide ratio. Depending on his altitude and the wind speed, he may not make it to his destination or even end up in the trees. In the second case, the paraglider takes into account the crosswind. This time he orients his canopy at a slight angle into the wind. This is called crabbing and allows him to stay on his heading and fly over point A. During flight, pay attention to conditions you come across. Adjust your trajectory early enough so that you stay on course and are sure to make it back to the landing field. Be particularly attentive during the approach and landing phases, as they require a great deal of precision. An air mass is influenced by winds and thermal activity. Since a paraglider flies within this dynamic environment, it's understandable that these movements will influence it in turn. Let's start out by defining the three rotational axes of a paraglider: roll, pitch, and yaw. First off, let's look at a model showing the pilot and the paraglider's combined center of gravity. It's located just above the pilot's head. This right-to-left motion, called roll, is induced by the pilot or is caused when part of the wing comes into contact with a thermal. The second movement of the wing is the pitch. It's the wing's forwards-backwards movement. Like the roll, it is affected by air mass movements or controlled by the pilot, though in this case usually as an exercise. In order to adapt your piloting techniques during the flight, two important aspects concerning the pitch need to be understood and recognized. Later on, during your training and under an instructor's supervision, you'll learn how to make use of the following pitch exercise. But first, let's explain pitch movement. The pitch increases when the pilot or a thermal causes the wing to increase the angle of attack. This movement is followed by a recoil which we call the surge. Acting like a pendulum, the wing tries to recover its position over the pilot's head. It will therefore have to accelerate to catch up. The stronger the pitch back, the stronger the surge. The pilot must be ready to brake. Pilots need to understand how this pendulum-like effect is created by the pilot and the wing. At some stage during your training, you'll be expected to practice these pitch exercises in stable air with radio support. The final rotational axis of the wing is the yaw. It includes all movements along the vertical axis running from the pilot through the center of the wing. It can occur on the ground when inflating the wing, or in flight when the wind suddenly changes directions, in the presence of gusts for example. As you progress through your training, you'll need to learn how to recognize and control these movements, which is called active flying. That way you'll be able to adapt your piloting, keep the wing over your head, and be in total control of your paraglider. Let's now consider the last stage of any flight, the landing. The landing involves two phases: the approach pattern, or simply called the approach, and the final, which is the last leg of the approach before landing. An approach pattern allows you to better position yourself in relation to the landing target by gradually losing altitude. The approach pattern is part of the flight plan that your instructor sets up before launching. During your first flights, it is never improvised. Before taking flight, you should visit the landing field to get an idea of its layout and specific features. There are three indispensable rules for any approach. First, figure out the direction of the wind on the ground. Use the windsock to orient yourself so that the last leg of your pattern, the final, is facing the